Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin, and I'm going to cover solutions by substitution and more in general, or more specific, homogeneous functions of degree alpha. So, if f possesses this property, f evaluated at tx comma ty is equal to some t alpha times f of x comma y, then f is homogeneous function of degree alpha. So what we have is we have a function that has multiple inputs, and I want to verify that this function right here is homogeneous of some degree alpha, and we'll figure out what alpha is in a moment. So in order to do that, I need to substitute in tx and also ty. So I need to evaluate this function here. And then if I'm able to pull out some t to a power, then that power is the degree. So let's do that. Let's evaluate this function at, we're going to do this at tx comma ty, and then see what happens. So this is the input cubed for this first components times this times the second component squared. So we're going to put a tx wherever there's an x, and then a ty everywhere there's a y. And then we will simplify this. So this is going to be t cubed x cubed plus tx times t squared y squared. And I'm going to have t cubed x cubed plus t cubed xy. And that means I can factor that common t cubed out. And then what I'll get is I'll get x cubed plus xy. Now notice that this is the original function, so this is t cubed times the original function f of x comma y. So this t cubed verifies that I was able to pull out a t to some particular power, and that power is going to be 3. So in this case, this is homogeneous of degree 3. Now functions that have this property are going to be nicer to solve in differential equations. So here's our differential equation, and I'm going to solve this by substitution, and I'll explain that in just a minute here. So in order to verify that substitution works, we have to show that both our coefficient functions are homogeneous of the exact same degree. So what I would say is my m function, m of x comma y, is going to be this first function, x squared plus y squared. And then I'd also say my n of x comma y is going to be the other coefficient function, which is going to be x squared minus xy. And I have to verify that these are both homogeneous of the same degree. So again, what we're going to do is we're going to evaluate these things at tx and ty, both of them, and see if we get exactly the same thing back. So tx, ty, and same thing here, tx, ty, and just see what we get. So tx x squared plus y squared, and then similar, this is going to be x squared minus x times y. All right, so we'll simplify the first one. So this is going to be t squared x squared plus t squared y squared. You can see that I can pull a t squared out, and I get x squared plus y squared, which is going to be equal to my t squared times my original function f of x comma y. So this is homogeneous of degree. That power right there is going to be 2. Similarly, this is going to be t squared x squared minus, t squared xy. I can factor a t squared out. I get x squared minus xy. And again, that's the original function. So this is t squared times, I said f, I meant m. And this is going to be t squared n of x comma y. So this n function is also homogeneous of the same degree because they're both degree 2. All right. If that is true, then what I can do is I can solve this through substitution. And the substitution we're going to do is we're just going to let y equals some u times x. So Let's solve this differential equation now that I've verified this. So let's get rid of this work and solve it. So we're going to solve this differential equation using this substitution. I'm going to let y equal u times x, and since these things are homogeneous of the exact same degree, what it's going to do is it's going to take this differential equation, which is not separable as it sits, because even if I try to put all my dx's on one side, all my dy's on the other side, with their corresponding variables, you're not going to be able to put all the x's on the left and all the y's on the right. But if I make this substitution, since it's homogeneous of the exact same degree, it will make something that is not separable, separable. So remember that I have to, just like in calculus, you can't just substitute for the variable y. You're also going to have to substitute for dy as well. So I'm letting y be equal to ux. So then that means our dy. So and dy, and this is really just a product rule. So the books usually write, the first times the derivative, the second times the derivative of the first, and the first times the derivative of the second. So I always went, derivative of the first times the second plus the first times the derivative of the second. So I'm going to write the same way they do. This was u dx plus x du, which is still just the derivative of the first times the second plus the first times the derivative of the second. So it's really nothing more than the product rule. Okay, now we're going to plug these things into our y's. So our y's, and then also our dy's. So these are going to go there. So what we're going to get is this is going to be x squared plus, y is going to be equal to ux, being squared, dx, plus x squared minus x times y, which is going to be ux. And then don't forget our dy, which is going to be, this binomial. So u dx plus x du. And this is all going to be equal to 0. So we're going to expand and simplify and then eventually separate. So this is going to be equal to x squared plus u squared x squared dx plus x squared minus ux squared times u dx plus x du. Now I'm going to have to FOIL this. So the first, this is going to be ux squared dx. Outside is going to be plus x cubed du. Inside is going to be minus u squared x squared dx. And then last is going to be minus ux cubed du, and this is equal to 0. So combine all the dx's. X squared plus u squared x squared. I also have this dx. This is going to be, should that be plus u x squared. Also this minus, this is going to be minus u squared x squared. And it's going to be equal to dx plus all your du's. This is going to be x cubed minus ux cubed du is equal to 0. And does anything nice happen? It sure does. So those will go away. And now I actually can isolate these things. So now this is going to be equal to, I can factor out a x squared, and this will be left with u plus 1. So x squared times 1 plus u dx plus, similarly, I can factor out an x cubed out of here. So this is going to be x cubed times 1 minus u du is equal to 0. And now we're starting to see that this indeed is going to be separable. I'm going to put all the x's on one side, all the u's on the other. So minus x squared times 1 plus u dx is going to be equal to x cubed times 1 minus u du. And I'll put my x's over here, so minus x squared over x cubed dx is going to be equal to 1 minus u all over 1 plus u du. And this is going to be minus 1 over x dx is going to be equal to, well, this thing right here. I'm going to break this apart because I know I'm going to have to integrate both of these. So minus u all over 1 plus u du. And now, like I said, these things were separable. So I can integrate both of these sides with respect to their variable. And I think I can fit it over here. So this is going to be equal to, the integral of this is going to be, minus the natural log of the absolute value of x. But on this side, this is going to be, the natural log of 1 plus u plus, now I'm still going to have to integrate this thing, but to integrate this thing, you're going to have to do a, well, usually we'd say a u substitution, but I guess I'm going to have to do a v substitution. So doing that, I'm going to have v is going to be equal to the denominator. So then dv is going to be equal to just du. So now this thing, this piece right here, is going to become minus, the bottom is going to be equal to v. Now the top is just going to be equal to u, so this is going to be equal to v minus 1. So then I can, I can break that apart into v over v, so minus v over v. Then minus this plus is going to be plus 1 over v. So this is going to be equal to minus 1 plus 1 over v, where v is going to be equal to 1 plus u. So plus, I have enough room? I might. So this is going to be minus 1 so the integral of this minus 1 is going to be, it's right this way, so this is minus 1 plus 1 over 1 plus u. So this is going to be equal to the integral of minus 1 is going to be equal to minus u, and then the integral of this is going to be plus the natural log of 1 plus u. Plus u. Plus c. So we can combine these to get two of those natural logs. So this is going to be minus the natural log of the absolute value of x is equal to two of these logarithms. So 2 natural log of 1 plus u minus u plus c. Now remember that we're not quite done because we have made a substitution. I want to, this solution needs to be in terms of x and y, not x and u. But I can just unsubstitute here, just like I unsubstituted here. So let u be equal to y over x. So then this has become, I'm just solving this for you. So this is going to be minus the natural log of x plus 2 times the natural log of 1 plus y over x minus y over x plus c. And that is a solution to this differential equation, really kind of verifying that when you verify this is a homogeneous of the same degree, that you get a separable differential equation. And just don't forget, like in Calculus 2, to unsubstitute when you're done. So if you like the content, please subscribe. Thank you.